Thank you everyone for coming. So today I'm going to talk about how we've internally solved the problem and basically how we avoid drowning in a huge volume of log data that we have internally from our test systems. To give you a quick bit of background about who Pure Storage is, we're basically a software company. We make and we sell high-performance storage systems. We actually sell physical hardware, so not in the cloud. But even though we make hardware, we're really a software company, because when you make a scale-out storage system, there's a lot of hard software problems in there. And so we've used a log processing pipeline, and of course, based on Apache Spark, to help us make sense of all that log data. So I'm going to walk through why we did this and how we built it, and some of the things that we've learned building this pipeline. Just a real quick, to give you an orientation, this is where our pipeline is at today. It's been running about a year now. We're at 2 million events per second that we process continuously all day. Actually, we were about 1 million events per second 2 months ago, and we just turned on a whole bunch of new test systems. So we were very relieved to see that it still worked once we scaled that most recent jump. We have a 5-second SLA, so we try to keep the pipeline from falling behind less than 5 seconds. We also read through up to a petabyte a day of batch queries, so ad hoc queries that our developers do, as well as look-back jobs, looking back in time. So we have a lot of data demands, and it's really all about how can we take all of this log data. Frankly, a lot of it isn't particularly valuable. But we don't know ahead of time which bits are going to be valuable and which aren't. So to set the stage, we really strongly have always believed in continuous testing. So we put a lot of effort in to building out a suite of tests, all from basic unit tests, functional tests, to large-scale regression and performance tests. And they're running 24 hours a day in a basically data center full of our test equipment. And we do this because, as a storage company, a bug that gets released to our customers could possibly mean they lose their data, which is a really big deal to us. And so we want to be really exhaustively testing our systems all the time, all different branches of code. And so we built, actually, I think, a pretty interesting, impressive system to orchestrate all of these tests. So we use Jenkins, we use a lot of custom Python systems to orchestrate each time someone commits a new piece of code. It runs through a series of tests before it gets onto hardware, and then it runs the right set of tests on our hardware. But I'm actually not going to talk about how we orchestrate that. What I'm going to talk about is how we make sense of all the data we get back from running all of those tests. Now, if you rewind 5 years ago, when we started this project, we were a small team, and you do things differently as a small team. We had a small number of developers. We all sat in the same room. We had a small number of test systems, a few racks of hardware, and one branch of code, because we didn't have a product, so we were all basically working on version 1. Now, when you do that, we were running hundreds of tests a day, let's say 200 or 300 tests a day. And when you have 5 test failures a day, you just email everybody. Someone's going to raise their hand and say, hey, it looks like maybe that was me. I'll go figure out what went wrong and fix it. That works at small scales, and I'm sure you can all see that that's not going to keep working. That's not a scalable system. But again, because it's a storage device that we're building, 5 test failures a day, we have to know and look into each one of those test failures. Because a race condition that happens 1 in 10,000 tests is still far too frequent for us to feel comfortable releasing that to customers. OK, so let's fast forward to a year ago when we started this project. Now we were over 100 software engineers. We have a lot more hardware, VMs, servers, and our own hardware that we make in our lab, our test beds. We have roughly 20 different branches of code, release branches, development branches. So we're running a lot more tests. We have a lot more features. We have a lot more tests we've written. We were running about 70,000 tests per day. Different kinds of tests, a lot of them in parallel, testing different things. Now, this is a number I think is somewhat impressive, but it's still too big. We have about a 1% test failure rate. So 700 test failures per day. Now again, we need to actually look at why that test failed, because there's no point in running tests if you don't go look at the failures. A little back of the envelope math says about 15 minutes of human time to look at, get on the keyboard, look around the logs, figure out why did that test fail. So when you do that math, you see that you're going to need a team of 20 full-time engineers to do triage. And I've done this job. I don't know if you've done these kind of jobs before. It's a terrible job. All you do is looking at other people's mistakes and trying to understand what went wrong. So one, it's not a fun job. But two, it's really expensive to have 20 software engineers who, instead of making our product better, are just trying to look at and understand failures. So we're based out of the Bay Area. That's an unaffordable way to use our resources. But to make matters even worse, we had the goal of doubling our team in the next 12 months. So this is only going to get much worse. So here comes the log analysis pipeline, and the motivation for it is, how can we make this system scalable so we can still run all of these tests, but we don't have to have so many humans in the loop? So the dream of our pipeline is to automate triaging of failures as much as possible. The key insight here is, of those 700 test failures per day, only about 25 to 30 of them are unique failures. The rest are duplicates. The reason that is because half the time it's an infrastructure problem. A switch is misconfigured, a link goes down, just problems in the data center. Not really test failing, but infrastructure problems that cause a whole rack full of tests to fail. It's surprising how many times we misconfigure VMs that are missing some package they need to run a test. But of course, we are humans, we are writing code, so we commit a lot of bugs. And when we commit a bug, it often triggers failures on multiple tests, because the tests are running in parallel, and because we don't fix the bug right away. So the bug is in the wild for several hours. So by realizing that most of these failures are duplicates, we decided to build a pipeline that will help us detect all of those duplicates. We still, today, have a human in the loop that creates the first, or understands the first instance of that failure and creates a signature that lets us detect the rest of those duplicate failures. So that's our primary goal, but there's a lot of other uses of that log data. Second one being, we want to extract performance metrics. We're collecting all kinds of interesting data about all of our test systems. Lots of internal metrics that we're collecting that, because we're doing all kinds of weird tests, we're running these systems a lot longer than our customer systems, are giving us interesting insights. So we'd like to collect this information and make sense of it. Maybe a developer turned on a new feature and wants to know, how often is it being utilized? Maybe it's being scheduled once an hour or once a minute. They'd like to know that question. And then there's questions that we can't predict. The end users of this pipeline are, at the end of the day, software developers, and they want to understand what's happening in the system. Maybe there's a performance regression that we don't detect until a week later after it's been introduced. So we have to figure out, when did this get into the system? Let's look back. What happened? And these are queries of the logs that, frankly, we can't predict. So we want to just make all this data useful in some format. Finally, of course, we're software engineers. We want to do this in a scalable system. I alluded earlier how in the last 2 months we've doubled the ingest rate in our pipeline. And all we needed to do was add more physical resources to keep up with that doubling. And that's what we want. The goal of any of these pipelines is you don't want to redesign the pipeline every 9 months to keep up with your growth. It should grow with you. Which is why tools like Spark are really nice because they can grow with you as your pipelines grow. And then because each time a bug is introduced, it will cause failures until it's fixed, we want these results to be relatively real time, as real time as we can get them, because that means we can get a quicker turnaround in the fix, or we can get a quicker turnaround in the prioritization. Sometimes we have a bug that hits once every hour, and sometimes hits multiple times every minute. So we'll suggest maybe fix that one that happens really frequently first. So we need results quickly. And stepping back in the problem of this log analysis, what we find in this case, as well as a couple of other internal use cases, is that you have a huge volume of logs. And when you look at the volume, only a small bit of it has a tremendous amount of value. But the tail of your logs, most of the volume, actually doesn't have a lot of value. It's easy to say it like this, though, because we don't know ahead of time which bits of log lines will be valuable or not. So our first step is, let's identify the ones we know are valuable. We can build alerts around them. Really simply, what this means is we have a log line that says crash. We know that means software crashed. We can take action and alert around that. That's the easy part. But then there's a whole lot of other log lines that are valuable and just need a little bit of structure. And a good example of this is our performance metrics. It's basically time series data. We know that if we put it in a time series database, draw graphs, it becomes much more valuable than just being text in a log line. And then finally, there's even more log data that is valuable and just the ability to search it. It doesn't have as much structure, but it's still got some value for our end users. But still, we're only looking at a very small tip of the log line. That's still 98% that we don't know what to do with. And as we've grown over time, we've learned more and more about the type of log data in our systems. So these areas that are valuable have grown, but we still have this problem of not really knowing, and that big tail of log lines, where the value is going to lie ahead of time. So the pipeline that we built, and I'll start with the generic view that I think is not particularly specific to our problem, which is how do you pull in all of these log lines, all these events, extract, transform, index, do expensive operations on the valuable part, but still make available the whole set. So we pull from log sources, which is all of our test equipment in our lab. So it's our devices, it's all of the test coordinators, it's all of the load generators, all of those systems produce different types of log lines. And we pull them in. So we augment all of those log lines and centralize them. We augment them so that we have the context so we can later do joins. So we know where that log line came from, what test was running, where it physically lived. And we store all of that data. And at the end of the day, what we want to do is build a bunch of ETL logic, build some reports, build some dashboards, be able to visualize this data. And the question is, how do we get from storing all of this log data to all the actually very interesting and useful bits? Well, the first approach we took was, well, let's index all of this log data. Let's use a tool like Elasticsearch, build an index over all of our log data, and then it's really easy to build dashboards and reports and alerts using that representation of the data. We did that, And we quickly learned that that indexing phase is a really painful bottleneck. This is really intense. We're doing a lot of work, a lot of which we don't need. So this became the unscalable part of our system, indexing all of these log lines. And this is well before we're at this 2 million per second that we felt this pain. So our first solution was, let's use a streaming buffer and a filter so that we only index a filtered set of our log lines. We're still storing all of the data in the bottom left, but now we're only indexing a small part of it. And this solves half the problem because now the data that we know, the log lines at the far right of that graph I showed earlier, are being indexed. But what about all of that mass volume of data that we don't know where the useful parts will be? Well, to do that, we actually built a system. And I'm skipping ahead a little bit here, but it's quite easy to do both streaming filtering and batch filtering with Spark. I'm sure that's not a surprise to everyone here that Spark plays a big part of this. But we built a system to refilter the data. So you see here we have a streaming pipeline that indexes the small subset of data we know is valuable. And then we have on-demand pipelines that will pull back. They'll look back over the last week or last month of data and re-index. And that gives us the ability to change our mind and say, well, we didn't think these log lines were valuable. We didn't index them, but we were wrong. We would like to walk backwards and index them because it turns out they were valuable. And that's turned out to be a really powerful way for us to find that balance, keeping all the data but not indexing all the data. And now we're putting a lot of load on the storage for all of this data, because we're both continuously writing new logs, new events, new data, but we're also doing all of these lookbacks and re-indexing, re-analyzing the old data. Now, we're a storage company, so we know how to solve that part. And I'll talk in a bit about how we actually did that. So this is a generic pipeline, and we found it to be quite generic. Let's focus on the left half. The right half, I think, is the use case specific logic. You're building a dashboard for your problem. We're doing triaging of test failures. We're looking at signature matching. So we have basically built regexes that say, this is how you uniquely identify this bug. And that all happens on the right half of this graph. The left half is just making sense of a huge volume of logs. So this is all somewhat abstract and bubble. So now let's talk about specific technologies that we are using in our pipeline. First one of which is rsyslog. This is how we extract, augment, and centralize the log lines from all the different components in our system. Now, I will tell you, just anecdotally, this has scaled fairly well, but this is actually a pain point for us today. And we're looking at a better solution to that. And it really comes down to the fact that we will still lose log lines occasionally whenever we have crashes, restarts, or other non-normal functioning events. So every day, we miss a few signatures because we didn't get all the log lines. So we're looking today at what's the better replacement for rsyslog. We don't have an answer yet, but as we've scaled, this has become a pain point. Moving on from there, for the storage of all the data, we are a storage company, so we happen to have on hand a very good solution to this, our product. So it's a scale-out file system or object store. But for the purposes of this presentation, it's just a file system. It happens to be a scale-out file system. So we use that to store all of the log data. The streaming buffer is Kafka, and that's worked really well for us. Now, as the least surprising part of this pipeline, we use Spark to do the filtering. Now, I called that box filtering. We're actually doing a little bit more than just filtering. We're doing transformations, some joins, a little bit more interesting logic to put those log lines in useful formats and do matching based on our filters. But it's Spark streaming to do filtering of the log lines. And then the refilter part is basically the same code running in batch mode. And that's a really big win for us. It doesn't add any extra complexity to our development process. And the final part that I want to talk about in detail is the indexing step. And this, I think, is probably the most surprising. Our choice actually was a file system. Now, we could have used other tools. We could have used tools like Elasticsearch or Splunk. We could have used databases, NoSQL or relational. There are other ways we could have done this. But when we looked, all of those other solutions required us to build another system, manage it, upgrade it. I mean, this is a production system, so that's extra complexity. But we already have the file system. We already need that for the storage box. And we realized we could reuse the file system also for the index. I'll go into a little bit more detail in the next slides about actually how that works. But that, I think, is the most unusual or surprising part of this pipeline. And then finally, all of the use case specific logic is basically custom Python code. And we're connecting to InfluxDB and Grafana to make the data useful and visualizable. But this is the part of the logic that is tied to triaging failures. So this is where we have a human who is basically trying to generate a regex that will help us automate finding all the duplicates. I'm not going to talk into detail about this because I think that's really specific to our use case. So let's zoom in on that indexing step and why it works to use a file system to index this data. OK, so the file system is unstructured data, but it's not really unstructured data. You have directory structures, and you have file names, which encode a lot of information. That's a structure that you're putting on the data. It's flexible, it's loose, it's not tied to a schema. We can change it, but it gives us a valuable way we can structure our data. So that's what we do. For the raw data, we use a directory naming format for our hosts, the year, month, day, and then the files per component that we're collecting the log files. A pretty straightforward directory organization. And again, the producer is our syslog that writes into this format. And the consumer is our batch Spark jobs that go back and read the raw data, either because we want to reindex the data or because a developer fired up PySpark and had some strange query that they wanted to ask about what was going on in our systems. They can do whatever they want. The index data, the more interesting data, is actually stored with a pattern, which is basically which signature did this match? What filter in the previous logical diagram triggered us to save this section of log data? And then we add the organization about time based on that. So this means that at a really high level, if you just ls that directory for each pattern, you can see all the matches for a given filter. That's a really high-level version, but we're doing a query when you're doing an ls. So we use file system tools. We use a file system to build a database. Now, here the producer is the Spark streaming. So this is what the Spark streaming job outputs. And the consumer is all of our downstream Python services that do the signature generation and matching and hook into Jenkins and Jira and all of our bug tracking and management tools. On the querying side, we're using NFS. NFS is a standard network file system. Every Linux machine in existence, well, at least modern one, supports it. natively out of the box. And we have less than 1 millisecond latency, so we can do queries quickly. Except doing LS operations and enumerating these file systems is actually still really slow. And the reason for that is the NFS client, using a network file system, is actually slow because it's serialized. There's no parallelization there. It's built, frankly, 25 years ago, where you didn't write things in parallel. You just wrote things serially. So it's actually still really slow. But our solution is to use user space libraries with libnfs so we can do parallelized queries. So we can speed up standard file system operations and make our queries respond 1,000 times faster just by parallelizing simple operations like ls. And lastly, we build buffering systems so that we're not latency bound. We're throughput bound when we're running the Spark batch jobs or when we're writing out from Spark streaming. So we build buffering so that we're not tied to latency, because latency is not what we really care about when we're talking about millisecond latency. We're talking about detecting bugs within minutes, and that's a different scale. Now, the reason why we can use a file system here is because we have a scale-out file system that has no limitations on the number of inodes, number of files, number of directories. That's a requirement. It has to be scalable. The other requirement, it has to be inherently parallel on both sides. The file system has to be parallel, and the tools that you use to query it have to be parallelized. So let's look, to end this, at actually what the pipeline looks like from an infrastructure perspective. So you remember we have all of our different components, each producing different types of log lines. We pull them out with our syslog. And that's roughly 24 terabytes a day. And the key to this diagram here is our syslog is 6 nodes, 16 cores each. That's our syslog cluster. It's all running in Docker. All of our clusters are running in containers. And of course, we are writing to a FlashBlade, which is the product we make. So this is a nice eating our own dog food example. We're making the FlashBlade better by using a FlashBlade. So that's appealing in its own way. And then after that, we're actually outputting 72 terabytes a day into Kafka and Spark streaming. That's because we're augmenting and adding a lot of context to each individual log line so we can make sense of it later. And then finally, a much smaller set of data is output to our custom tools, because it's really only the failure scenarios that we're looking in more detail about. This is the indexed data, basically. Those connect with our Jira and bug tracking tools. And then the batch side of it is another Spark cluster that does the lookbacks and the refilterings. And we have another cluster that just lets developers spin up a PySpark instance. Most of our developers prefer that. So they can run ad hoc queries about features they've introduced into the system. So all in that same storage system, we run our syslog, Kafka, and the Spark jobs. And we use Docker and containers to manage all of our compute resources, and our own single FlashBlade to manage all of the storage resources. So in our journey to build this pipeline, our key takeaways, which basically means things that we learned the hard way. The first one being, index only what you need, but store all the rest. And this is really, I think, the most important point for how we're able to think about a pipeline in a scalable way. Second one is optimize for throughput, not latency. We're doing this in massively parallel systems like Spark. And so throughput and both writing and reading all this data is really what matters, not latency. And the final takeaway is disaggregating the compute and storage has made it really easy for us to evolve and iterate and change. Because this pipeline has gone through many iterations and many different scales. Now, this disaggregation is actually the norm in cloud providers, but in other on-premise environments, it's not. HDFS-style approaches are still the norm. And that has a lot of rigidity and pain associated with it that you don't have when you use something like Docker to manage your applications and a shared storage that can scale out on its own independently. And this has really helped us in the development process of the pipeline. And with that, that's how we're so far successfully managing to make use of all of this log data and keep our systems up and running. Because this is now a critical system. Every day, someone is complaining, why is it so slow? Why is my failure not detected? Every day, someone's complaining, which means it's now a critical piece of infrastructure because people notice whenever anything goes wrong. So we have a new set of challenges. I'm happy to take any questions about the pipeline that we've built, our experiences. I'll also hang around in case you have questions that, okay. All the way on the other side from the microphone.
What about compression? Do you use some compression?
Yes, so the question is about compression. The actual storage product that we have, our FlashBlade, actually does inline compression. So behind the scenes, our product is compressing the data. So we store the log files on the FlashBlade, and it looks like they take 5 petabytes in space, but in reality, they only take 1 petabyte of space because we're compressing behind the scenes. Now, there's another interesting point about compression, which is Kafka. Because actually what we're finding is now in our system, one of the biggest bottlenecks is just the amount of data that's going over the network. And so we're finding it's valuable to compress just because that lessens the load on the networks that we have internally, because the volume of data is so much. So we compress to save networking bandwidth, but we rely on the storage layer to compress when we're actually storing the data.
Are you doing any kind of automated classification of those errors, on the fly?
So that's a good question. So the question is basically, is there any automation of these error detection? And that's actually an in-flight progress. So if you look back at the diagram that I have, if I can backwards, there's this custom logic that's in Python now, which is basically a human in the loop. So we don't have AI, we just have HI, if you will. And we're looking at ways to put machine learning in there so we can even further reduce the amount of touches a human has to do. Think about automatically creating a regex to identify a failure. But that's all in progress. Today, we're still having a human create those signatures, but we are working on how we can automate that process. So that's an in-flight process. But just like most AI projects, you need to get the data pipeline set up so you could ingest and collect the data, and then you figure out how you can design algorithms that actually make sense of that data automatically. So we're working on it. We're not there yet.
Can you tell us a little bit about any issues you faced especially with Spark streaming, maybe its integration with Kafka? Did you have any problems there?
So the question is, do we have issues with Kafka and Spark streaming? Frankly, no. I mean, we've had issues really related to monitoring and just making sense of what's going on and making sure it's doing what we expect in terms of keeping up with our ingest rate. But that's, frankly, kind of on us, because we're software developers. We're actually writing the code, the Java code that sits in Spark. We use Java. And sometimes we don't do a good job. Sometimes the code can't keep up. And what we've had problems with is, how do we alert? How do we detect when we're slowing down, we're not keeping up with the pipeline, and why that is? So a lot of those problems are really just monitoring, I would say, and making sure we understand how the process is working.
Do you not have any issues with duplicates or missing data?
So we've had issues with missing data, but that's further upstream. So all of our missing data issues are really to do with our syslog. So that we've had that problem definitely, but not with, frankly, with Spark and Kafka. And I haven't shown you all the iterations, but we've used another 7 tools that have been tried and thrown out. But those have been solid for the most part. Not perfect, but we can work with them.
So this is a really impressive solution. If you have a use case that this kind of implementation is for cloud, what probably you can consider instead the storage or the index solution that you?
Yeah, I think for the cloud, the part that really changes is the storage part. I think, right, and the storage that we're using for the index is really the part that's most unusual. And I think I don't know of a cloud service where I would recommend doing the same thing. And so what I would probably have done in the cloud is stand up another database. Maybe it's Elasticsearch, maybe it's Mongo, maybe it's something else, but I would have spun up another cluster and had to manage it, but it's what I think the only place that it's really different is right there.
First of all, thank you for such a nice presentation and the food yesterday. So this 70,000 tests which you do every day, it includes unit test also, or just integration test, stress test, performance test, end-to-end tests?
So well, it's now 120,000. So that does not include unit tests.
Okay.
So it just includes tests that are of the full binary, if you will. So basic regression tests, basic functional tests, as well as larger stress tests and performance tests. And the unit tests produce a much smaller amount of log data and run in people's laptops, so it's a little bit different.
And one silly question, I think. So Jenkins tells you how many issues are there already, and your system tells you how many errors it found. So so you said about some people complaining that their issues were not found. So was it not easy to see that your system found, let's say, 670 issues and Jenkins says 675 issues, so 5 are missed out by your system?
Exactly. And so not all of them are detected. They're just, we know there was a failure, but we didn't detect a duplicate there, but there really was a duplicate. And that's either a problem of the signature didn't match, it wasn't done correctly, or we lost log lines because, as I mentioned, sometimes our syslog will drop log lines, and so we didn't match the signature because we didn't have the data. And that's really what the problems are. So we know it's a failure, we should have been able to tell it was a duplicate, and we didn't.
Thank you.
Do we have? It's the last question, but then I'll hang around for a little bit afterwards in case there are more. I keep jumping over this platform.
Yeah, just be careful. Thanks for the presentation. Very interesting. When you are indexing the data, you put a path there, and then you put the data files. I'm curious about what are you storing the data files? Is it the whole data or a subset of the data when you index it?
So when we index the data, what we're actually storing is a subset of the data in a Parquet format. And it's a structured interpretation of the log files. So it's not fully indexed, but it's put in a much more easy to query format, so you can really easily use Spark to run queries on it. So it's post-processed Parquet format, but just as a file. Thanks, everyone.